Welcome everyone to the third video of the week, Energy and Material Consumption and CO2 Emissions. In the previous video, we understood the importance of closing the mass balance. Moreover, we saw that carbon dioxide emissions are not the only ones that may produce an environmental impact. Today, we are going to talk about the importance of energy efficiency in an industrial plant and the overall importance of closing mass and energy balances when evaluating the overall performance of an industrial process. Do you remember this slide from the previous video? Our pulp mill converts wood into bleach pulp. Other inlet streams are needed, water used in the process, and utilities like steam or cooling water that provide specific services. And other outlet streams are generated apart from the product. These are gas emissions, liquid emissions, solid waste, and losses. Utilities provided from an external source, as represented here, once they are used, also go out from the process. As we saw in the previous video, utilities can also be generated inside. Do you remember what utilities are? They are ancillary services needed in the operation of any production process. They can be fluids for heating or cooling, like steam or cooling water. Also fuel, processed water, air, and other glass supplies that are inlet streams to the conversion process and or to the auxiliary units. And of course, electricity. We recall from the previous video that in purple, the main conversion process is highlighted. In green, auxiliary units, and in orange, utilities-related units are pointed out. Do you recall that we mentioned that electricity is not a mass stream? Observe in the figure the dotted line streams, in orange, corresponding to the energy-related streams. From the boilers, a steam flow transfers the heat from the combustion of waste streams into a gas turbine to generate electricity that is used internally. The electricity surplus is sold as a byproduct. Sometimes, mass streams are needed to transfer energy. Inside the process, internal reactions may need or produce heat. Also, reactions take place at different temperatures, and products and byproducts are customized to be sold into the market at specific conditions of pressure and temperature. The system has to accommodate the heating, cooling, and electricity needs. In an analogous way as in the previous video, we talk about mass losses, like purges. When dealing with heat streams, not all the heat can be transferred. It means that there are also heat losses. You will learn more in video 1.4. Are you ready once again to remind your thermodynamic lectures? Energy cannot be created or destroyed. Therefore, the inlet energy rate is equal to the outlet energy rate. In the expression of the image, for one-dimensional and steady-state system, Q is the heat rate, W is the work rate, M is the mass rate, and H is the specific enthalpy. An energy balance can be used to evaluate how much energy is lost in a system, as in a plant like our pulp mill. Do you recognize the definition of the specific energy consumption from video 4.1 in the first of the MOOCs? In industrial plants, remember, the main output is not an energy stream. The specific energy consumption takes into account the energy used per unit of activity. In our pulp mill example, per ton of pulp produced. If the process efficiency is improved, it means that if we consume less energy per unit of product, the specific energy consumption decreases. This implies, of course, energy savings, as well as energy security and less indirect emissions. How do the climate change mitigation options described in the first video affect the specific energy consumption? Let's take a look into that. By changing the used raw material and the conversion process, we may decrease the overall energy needed per ton of pulp and or increase the amount of synthesized product for a fixed amount of energy use. Via process integration, the amount of external energy needed decreases per ton of synthesized product. Through an electrified process, the overall electricity used per ton of pulp may be lower or higher. However, the emissions allocated to this new electricity consumed should be lower. Climate mitigation measures not only affect the energy streams, as explained in video 1.1. Material efficiency can be defined as the ratio between the material used and the material supplied. In our pulp mill case, mainly the ratio between the wood used to produce the pulp and the wood supplied to the plant. Indeed, if less fuel is used for non-energy purposes, the lower the environmental impact. An improvement in the efficiency of the conversion process will increase the material efficiency. The mitigation measure that relates the most to this performance indicator is the change in raw material and in the conversion process. Both numerator and denominator can increase and decrease respectively. Let's then take a closer look at our pulp mill streams. The decrease of the specific energy consumption and the increase in the material efficiency will allow a decrease in inlet resources, which will be translated into a decrease in process-related CO2 emissions. In the case you are wondering where carbon capture and storage would have a role, it will capture the CO2 emitted, highlighted in the image, virtually not emitting any CO2 at the end of the process. I said virtually because boundaries matter. Do you remember Scope 1, 2, and 3 emissions from the first MOOC? In the slide, you can see larger problem boundaries, being our pulp mill the last conversion step. It is indeed important to close the energy and mass balances to have a full and reliable picture of the inlet and outlet streams of the plant and how they are particularly linked to the CO2 emissions. In the next videos of the week, you will dive into the different mitigation options. Enjoy, and thank you very much for your attention.